Swayam Prabha. Digital India. Educated India.
So far in the course, we have looked at many different concepts which are helpful to design mechatronic systems, various kinds of mechatronic systems. Now we'll see some kind of a case studies to see how whatever we have learned can be put together to build some innovative kind of a systems. Okay, so we'll go through some of the research examples from our lab, and we'll talk about in more details how these systems can be really built by using some of the concepts that we have learned. So let's start with these. This is a lab called Suman Mashruwala Advanced Microengineering Lab that we have developed in Department of Mechanical Engineering, IIT Bombay. And this lab, I must acknowledge the funding by our alumnus Raj Mashruwala. At that time, about 2007, we developed this lab with a funding of about $1 million from this alumnus. And beyond that, a lot of activities have happened in the lab, and a lot of new projects have come, and the facilities got extended and things like that. So here is we started our activities. So before I begin, I'll acknowledge these all the researchers, all our PhD students and MTech students and RAs who have contributed to this work, and of course the funding I mentioned about. And there are many other grants that we received later for the research that we are going to see about. Okay. This is roughly some outline of the talk. Right now we'll use this for 3D microprinting purpose, the technology called microstereolithography. I'll talk about it. Similar to our 3D printing in SLA kind of a technology, but I'll talk about that, and then we'll see what are the novelties that we have come up with, and how some of these mechatronic concept we have integrated into these systems to make sure they work the way we would like to have them work. Okay, so this microstereolithography is a simple technology of 3D printing. We start with the CAD model in the software, and this CAD model, as you see here, is then software sliced into different slices. Okay, so this is a software that we have developed in-house to create these slices from this CAD model, and then further these slices are divided into the lines for the scanning. Okay, so each of the slices will be scanned by this line, and now if the idea is to run the laser along this line, so that the photopolymer resin will get cured only at this part where the laser is scanned, and laser needs to be getting switched on and off at these data points. Okay, so this is how the requirement for the 3D printing in SLA kind of a way is. Similar to other kind of technologies that also exist for 3D printing. Okay, so the when you scan, you get this kind of a final product out of this system. Now the question is when you want to do it at a microns kind of a scale, okay, the scanning becomes very important, and the scanning system needs to have much better accuracy at a submicron kind of a scale. Okay, so this accuracy can be provided now that we have gone through this course. We know that for a very high precision motion, the compliant mechanism stages are going to be useful. Okay, we have seen that in the CD-ROM kind of example. Okay, so we developed this concept for the compliant mechanisms later for this scanning purpose. But to scan the laser beam, there can be different kind of methods for scanning. Okay, so some of these methods are kind of demonstrated here. So you can have these mirrors which are kind of tilting, and then the lens is focusing the laser beam, and then as the mirror tilts, the laser beam is going to scan on the surface. Okay, then you can have the laser beam scan, and then the lens's placement is now different than this kind of a method. And then in this case, your tank itself is moving, the laser beam is stationary. So each of these systems have some advantages, disadvantages one can see. For example, this system, if you see, the scanning goes over the sphere, and your actually the surface on which the photopolymerization happens is flat. Okay, and this is what happens is, like, the then laser gets defocused at the other places, and when you want to create a micro scale kind of a component, you need a laser focal length to be very, very small. Okay, so that the focal spot is small in size, and for such a small kind of a focal spot, then this becomes very difficult or infeasible to move this mirror and still keep some reasonable kind of a resolution of the component here. Okay, because as the laser gets defocused, the resolution gets compromised. So we proposed like a new way of scanning laser beams. We actually proposed two ways. One of these is this, but this is also better than all the other methods, but it's not great kind of a method of scanning the laser lens here itself in the linear kind of a fashion. Laser is fixed, but the lens is scanned in the linear fashion. Okay, this we proposed first, and then, like, we said that it has some kind of a benefit, but it's not great. Then finally we proposed another method which we could get an Indian patent on, is scanning the laser beam along with the mirrors. Okay, so mirrors also get scanned in a way that in the linear fashion. Okay, so previously we were moving only lens in the linear fashion, but now lens and mirror one, they move in the linear fashion, and you get a laser beam scan on the surface. Then you can see that the focal plane, all the time the laser focus remains exactly at the focus. Okay, laser remains exactly at the focus at the entire point on this plane, and the same thing can be done with the other direction also. Okay, so x and y direction scanning can happen in this kind of a fashion. Okay, so there are many advantages, that your spot characteristics remain uniform, so you can increase the range now, whatever dimension you want to scan, you can get that kind of a scanning done, and that's why there is no limit on the range, and you have improved resolution happening with this kind of a scanning system. Okay, so now to do this scanning in a very precise kind of a fashion, then we need stages. Okay, so the entire system would look something of this sort. Okay, where your beam is used and split by using this acoustic modulator, which is basically a switch. You can imagine that. Okay, if some signal is given, electrical signal is given to this switch, then it will switch on the light and switch off the light in a matter of like few nanoseconds. Okay, so that is what the acoustic modulator is designed for. Then your beam is getting focused on these fixed mirrors first, to kind of they are just steering mirrors, and then you have actually mirrors which are in motion. Okay, so these are the mirrors that can be used for some adjustment and alignment and those kind of purposes. Okay, so this is how entire system will look like, and you will need to move now these mirrors M1 and M2 to have this scanning happen. Okay, mirror M1 and lens together will move, and then mirror M2 will move in a perpendicular direction. Okay, to this laser beam with a integrator, like mirror 1, mirror 2 and lens unit together will move in this perpendicular direction. So that's how the XY scan would happen. Okay, so these are the two perpendicular direction motions that will be happening for the mirrors. Okay, so now to get to this with the submicron kind of a precision, that's what I was talking about. We need some kind of a compliant mechanism design that we saw. Okay, so you remember this concept we talked about. You have a you want to move this block by using some kind of a compliant mechanism. You start off with simple kind of a scale or cantilever beam which is fixed at one end, and you give the deformation. The beam moves in the vertical direction, but there are these parasitic errors, that there is a tilt here and there is this kind of a parasitic error. Then you add one more beam to that system, and then you will find that this will be now better, that it has no tilt that is happening to this block, but there is still this kind of a parasitic error exists. And then you go for this system where you have this block moving in perfect straight line because of the symmetry. Okay, so there are some more nitty-gritties about the system which we will not get into. There's a whole lot of kind of research has happened over these stages to see how their analysis, how their behavior is, especially for long deformation or large deformation. So this idea we implement by using developing this compliant mechanism or flexure stages. Okay, and these are now further manufactured by using assembly route. Okay, instead of doing like typically people fabricate such mechanisms by using some kind of a monolithic block cutting out of that in mortar jet or some kind of a EDM kind of a machining, but we proposed a new way of doing it by assembly route, so that we get mechanisms which are also can be built in the third dimension. Okay, and we save some kind of a costly processes. So this assembly route is not very straightforward. If we start like doing what we have fundamentals that are known in mechanical engineering, that you assemble two pieces together, you need two pins to locate them with respect to each other. We start doing that, and you will find that this mechanism would conventional principles, if you do this mechanism will get warped. Okay, actually if you see, this is a picture of the warped mechanism where all the pins are put in all the places, and this warping happens. And this warping happens because these beams have a tendency to flex, okay, or the tendency to move. So depending upon like small tolerances, even if they are very very small, you'll have this tendency for the internal forces to be created when you put these multiple pins. So we have come up with guidelines which will formal guidelines which will resolve this issue and give you number of pins to be put at places, so that the mechanism eventually becomes unwarped. Okay, there is, so the same mechanism, same tolerances on the pins and dimensions are there, but now in this case the mechanism is not warped because of the particular kind of a way of assembling. Okay, so we have some publications on this idea. Okay, so we use that, and we build complete flexure stage, and this is like a complete scanning system. So this is one stage is carried by the other stage. So this is say X motion stage here, and then you have this Y motion stage inside this, and here there are some kind of mounts for the mirrors, and here there is a mirror mount, and the beam is getting kind of steered by these mirrors, and it is going finally on other stage or Z stage tank, which will be getting moved in up and down direction for the different layers that you want to prepare in the 3D printing. Okay, so this is a system that is now built, and now these flexure compliant mechanism stages are available. Here you can see that these are some of the Mechatronics components here, where your mechanical compliant mechanism stages are integrated with these voice coil actuators, and then there are linear encoders to do the job. Okay. Then we have now these compliant mechanism stages are manufactured by this company called Flex Motion Technologies. It is a startup from here, IIT Bombay, and they are now available for many different applications. Okay, so now we integrate this mechatronic system for the 3D printing around this. So we have this data acquisition system called DSpace. Okay, so this is 1104 particular version of this DSpace company microcontroller, and they provide basically this kind of a hardware interfaces as a Simulink blocks in the MATLAB Simulink file. Okay, so these are now extra blocks coming in the file. So what you can do is basically whatever controllers that you built by using Simulink or any other kind of a way in MATLAB, they can be very easily ported to a hardware system. Okay, so that's a ease for very fast prototyping. You can do this. Okay, although this is a costly kind of affair, but once this system is available, you can do a lot of mechatronic system prototype testing very fast. Okay, because you don't need to worry about programming a microcontroller, because these are already available as block sets in the Simulink block. You can just put together those blocks and you start programming. Okay, you start building the thing, and all the things programming will happen automatically for this microcontroller. Okay, they have developed this kind of a the block sets which will compile and build the microcontroller program the way you have maybe if you have taken hands-on training, you have written some program in TIVA. Those programs will be built now by a compiler in real-time system of a MATLAB. Okay, so this is a very handy tool for especially those who are bogged up by this microcontroller programming business. Okay, and this is good, like fast prototyping way of doing things. Then we in this board we need to identify what are the channels that we need to use. So we are using here the digital to analog converters, two converters for this driving X and Y stages, DAC1 and DAC2, which has this amplifier that is used. So this again, so as we have seen for any high current or high power application, you need an amplifier to be there to interface with the microcontroller. So here we are using this Quasar amplifier for X and Y stage voice coil driving. Now this is we are using here voice coils as we have seen here. Instead of motor, we have this something called voice coil. It's just a coil and a magnet assembly together, and these are non-contact actuators. They are guided by these compliant mechanisms, and only the magnetic force is applied when the current is passed through this coil. Okay, non-contact kind of a fashion force. Okay, no friction is there in the system. Then you have this encoder, which are kind of sensors in the system which are reading the data. We have seen a lot about encoders, how they work and how they can be programmed and things like that. Okay, so these are optical encoders, but now they are linear kind of encoders. Again, they are non-contact, and so entire system has no friction, and that's what gives us a way for positioning them with a very fine accuracies. Okay, and then we need this laser to be switched on and off. Okay, at certain locations, so depending upon what you are scanning. So this is a RF driver for driving this acoust-optic modulator. So this entire thing comes as a one unit. Acoust-optic modulator will come along with this driver, and you have some kind of a DAC pin which will control the laser intensity. Okay, digital to analog kind of a converter. Depending upon this analog voltage, your laser intensity will be controlled. Okay, so this is a system that you need for operating laser on and off depending upon XY position, so that your scan gets done in a manner that you would like to. Okay, so there is one more kind of a DAC that will be used for Z stage, for giving the Z dimension or like third dimension motion. So this is how you integrate. Then typically you start with testing of the systems and characterizing the system. So this is how we have characterized the power of the beam that is coming out as input voltage to acoust-optic modulator is changed. Okay, So this you get a laser spot which is now changing it can be changing its power depending upon what is the voltage that is given as input to AOM. So if you want to switch off the voltage, you give 0, and if you want to switch on the beam at a certain point, you give something like 0.6 volts or something like that to kind of get that much intensity for the laser beam. Okay. Then we test the XY stages at different scanning speeds, and here this scanning speed is about 0.8 mm per second. We have gone now for the stages which are running at 15 mm per second or 10 mm per second kind of a thing, and currently we are building other kind of a resonant kind of a scanning stages which are going to the speeds as high as 300 mm per second, so that with keeping the same accuracy. And you see that position accuracy achieved here is about 200 nanometer. Okay, so this is how one can develop the system which can give you the accuracies which are sub-micron level when you want to do like a micro printing, okay, or micro scale printing you want to do. Okay, so with these kind of accuracies you are able to kind of get your components really fabricated really nicely. So this is like a entire complete system developed. One of my first PhD students, Suhas, who was working on this in the early days. Now we have, I think, the fourth prototype of this micro printer coming up in our lab, which is having very high speed and high range of component that can be fabricated. Okay, so we can see this little video of the entire system here now. So you can maybe we'll show you in the next video. Okay, then we have another video which is coming up here. Okay, so this system has this is like a next version of the system. You can see here this is electronics, they are interfaced, and there is a mechanical scanning system, and this mechanical scanning system starts scanning XY stages by using this compliant mechanism and voice coil kind of actuator. And you can see there is this is a tank here, and then there is a Z stage on the top of this. Okay, so this Z stage is what is carrying the component up in the Z direction. Okay, so once the component first layer gets printed like this, okay, so this is a layer getting printed, so there is a continuous motion in the Y direction and stepping motion in the X direction that is happening here. Okay, and this component gets slowly developed here. Okay, so this is like a hexagonal kind of a comb kind of a structure. Okay, honeycomb kind of a structure. Okay, so this structure is getting developed now, and then multiple layers of such structure can be developed. Right now we have kept only for the demonstration purpose, the Z stage is not seen here, but this layer, once it is fabricated, it will be pulled off the bottom resin vat, and then the next layer of the bottom resin will come between the fabricated layer and bottom surface. Okay, and once that happens, then you'll have next layer preparation done, and next layer can be fabricated in a similar kind of a way. Okay, so let's move on to this and see some of the components which are fabricated now with this printer. Okay, so this is now doing the layer by layer. It is moving it is pulling the component up and then again going down and positioning itself to a level where very thin layer of the liquid is squeezed between the component and the bottom of the resin vat. Okay, resin tank here. Okay, like that, multiple layers, it will start fabricating these components, and you can get these components fabricated like this. So this is a honeycomb structure that you saw getting fabricated, and multiple layers, so you can get thick structures like that. Okay, so many structures which are very intricate geometries at a micro scale can be fabricated. So Now we are using this new concept of resonant vibrations to do now the similar kind of displacement or scanning at a higher speeds. Okay, so let's move on from here to see actually the structures fabricated. These are like different kinds of structures that are fabricated by these, and you can see these scanning electron microscope images of these structures, which are showing like very good dimensional accuracy with respect to the accuracy that we wanted to have. Okay, so one can fabricate these high aspect ratio microchannels and many different kind of structures that can be fabricated. Okay, so I'm just displaying these structures to see. So one can see these are 48 layer kind of a structure. So 48 times like Z edge has stepped up, and you get this entire structure, and inside this you can have whatever geometry of the nozzle that is needed can be realized. Then you can have a boundary scan. So these are all what you say more kind of refinements that are done based on the application requirements. The basic mechatronic system remains the same, like you have these XY flexure based scanning stages, and there are some kind of interesting control algorithms that are needed to be used for this kind of a scanning, because you don't want to get into vibrations of these compliant mechanisms. Okay, if they start vibrating unwanted kind of a way, then you'll start seeing the inaccuracies in your positioning. So those are all handled at the control level by designing some control strategies which are I would say unique to make sure that these vibrations don't creep in from the compliant mechanism stages. Okay, and still we achieve the job that is needed at high speeds. Okay, so that's where like a lot of these modeling and simulation and fine tuning of the gains, those kind of activities would be coming in as we have seen in the course. Okay, so this is like constrained surface kind of a fabrication, where your now top surface is constrained instead of so what we saw in video was actually this. Okay, the top surface was constrained, but the Z stage was like upside down. It was Z stage was coming up rather than going down in this kind of a way. Okay, so this constrained surface can give you very high accuracies in the layer, because the layer is constrained between two surfaces, and the surfaces can be maintained at a desired accuracy. Okay, unlike open, without constrained surface, you will have open layer, liquid layer, and liquid layer top surface we don't know whether it will have exactly the same dimension as the thickness that you want to get cured. So this constrained surface microscopography gives you quite good accuracy in the component produced. So this is conclusion for this part, where we see some novel way of scanning laser beam in the linear fashion on the substrate. So it's like that you can think about your own idea of some kind of a way, some activity to be done. Okay, once that idea is there in your mind, okay, then you start putting things together around that idea. Okay, so we started off okay, we wanted to do some high accuracy kind of a thing. Then this idea came up of the new way of scanning laser beam, and then we started putting things around that idea. Okay, this is how you can see this mechatronic system can get designed and built in a very nice way. And whatever there's some kind of you'll find some things come along way. Like say for example, in our case we found that okay, how do we assemble these beams very easily? That was one of the important kind of aspects. So that we resolved by formally studying how this assembly is behaving, and so the small experiments, okay, very crude experiments help in getting these ideas generated in a faster pace. Okay, so we started assembling and we find, okay, oh, look, you have this problem. Then we study this problem in little bit more mathematical details, and then give a solution. And then so going back from theory to your practical and practical to the theory, like that, that kind of way of doing things help a lot. So that's why we started off this course with looking at actually the practical systems, the way things work. If you remember, with CD-ROM and scanners and other stuff, more you kind of work with those systems and understand what is going on in there. It will help you to design like new things much better way. Okay, so I encourage you to really look at these some of these systems like CD-ROM or hard disk drives which are gone. You can just open them up and check out, okay, what are the components that are existing and why they are there, like that. Okay, as we did this analysis, you can carry out with many other kind of devices in the similar kind of a way. Maybe your washing machine, or like any other kind of a tape recorder, like a lot of these devices we may find available at a throwaway price, or they are gone without any cost. People will be happy to give you to explore. Okay, so see, this is the first kind of a step for developing this product. Like now we want to get into the product, then the further direction is to convert this kind of idea now with the microcontroller like TIVA. See, we have used DSpace as a data acquisition system. We cannot use it for actual product. Okay, this is just for the sake of prototyping. Okay, it's very costly system, and it comes with MATLAB. MATLAB, you don't have commercial licenses of MATLAB, you cannot ask your customer to do that. So this DSpace is not a thing for actually find the final product. For a final product, you need to go back to microcontrollers that we have seen in this course, like TIVA, where like you start programming this to get your embedded system completely done. Okay, so you need to kind of see, okay, what all things, components I need, what all these drivers I need. All these things can be integrated in a electronics box with some kind of a microcontroller. The choice now you can have based on this course, you can have different choices possibility. Many places you may need this human machine interface with some kind of a touch screen or something to operate the machine. Okay, so this kind of a product will be, so there are some microcontrollers which will provide you this. Okay, so in Raspberry Pi, for example, there is some possibility. In TIVA also there are some other kind of versions which are available in Texas Instruments, other microprocessors which will offer this kind of interface. Okay, and then we can program that to get the complete system as a product. Okay, so then like this comes to you as a product where there is some touch screen and you have some kind of a pen drive on which you can just put the data of what is to be printed, and it will start printing. Okay, the way we use our 2D printers in home, you can have this kind of a way 3D printer as a product can be produced. Okay, so this is first part of the thing. We'll stop here for now, and then we'll continue our discussion in the next part about some other kind of a case study system. Okay, thank you.